Welcome to 5 Steps to Creating Operational Excellence in Robotic Welding Automation. I'm Will Healy, Industry Strategy Manager for the Americas. You know, part quality issues and misproduction quotas can really sink our profitability. The same problems can repeatedly show up again and again, but with the stress of meeting our deadlines and hard delivery quotas, we really struggle to find time to solve the root cause of problems, and really find a sustainable answer that gets rid of the problem. In this presentation, we'll discuss strategies and technologies for improving uptime and eliminating nuisance stops from failed automation applications. So I'm going to talk about in operational excellence. Greg gave a great presentation on all the puzzle pieces that come together for operational excellence. I'm going to focus in this presentation on reducing waste, right fit and function, identifying trouble spots, controlling consumption, and really the root cause of failure and knowing the total cost of ownership. So with the demo that I have here in front of me, this is our weld cell demo. You could picture this like the A side of an AB robotic weld cell, right? The robot would be on one side welding while the operator is loading this side. We have identical sides on both sides, and this gives us some interesting opportunities we'll talk about later. But this is a weld cell for us. It's for a trailer hitch. And we're going to go through different sensor applications here. But the place I want to start is, how do we select the right sensor for the application? How do we find application specificity? We have weld spatter accumulation on sensors. Maybe we have the wrong technology for the application. Maybe we need better mounting solutions or a different position for the mounting of the sensor to be able to detect it. We got to think about the environment and how spatter and impact is causing us to have sensor failure. So when we're selecting, there are lots of options. You could see here what we consider our basic option for welding is a PTFE coated sensor. This one has a ceramic coating on the top, but it's one of the more basic sensors that we offer. And then we have other versions like over here, the Sun 73 coating on a steelface sensor is one of our most durable coatings, or the W51 coating on this flat pack steelface sensor. And then most recently we've come out with a black coating. You could see it here on this product card. The black coating is one of our most robust, newest coatings that we've released. Then, of course, you have, for impact damage, you have steelface. You can see a steelface with PTFE coating here. I already mentioned the steelface with Sun 73 coating. But a steelface is designed to protect the sensor from impact damage. We also have a special sensor called the bunkerprox. It's a really cool design because it's using an M12 circuitry inside an M18 housing. So the housing itself is much more robust. So if you have problems where the housing of an M18 standard sensor is getting sheared off or damaged, this is a much more robust housing because we're using an M12 circuitry inside an M18 housing to give us a much more robust housing. And so the bunkerprox is a great technology to be able to protect your sensors. Some people use photoelectric sensors in welding. It's not something that I recommend, but every once in a while the application warrants it. We have a photoelectric BOS23K product here that can be used as a background suppression to detect maybe a hole or a feature. Here's a through beam sensor. So you can see there's one here and one down at the other end, and we're actually shooting through a hole in the part to be able to detect, is the part oriented in a proper direction. And so a through beam, because the photoelectric's out of harm's way, can be a possible application. And then we have some very rugged photoelectric sensors. This one here has an infrared light. Infrared has a high gain, so it can burn through some debris and dust. And sometimes if we've got to get into a tight place, this is a nice through beam infrared sensor with a rugged metal housing to survive. And then last but not least, I don't want to forget, there's lots of pneumatic cylinders inside of a weld automated cell. And here you can see we have cylinder sensors doing extend and retract of the clamping cylinders. And so these sensors have weld field immunity, and you can see here silicone protecting the cables themselves. A lot of these cylinder sensors have real tiny fine wires on them, and so one tiny weld BB can completely destroy a sensor or just destroy the cable, but the sensor's still good. So we're replacing sensors that aren't actually failed, the cable's failed. So by protecting the sensor cable on the cylinder sensor, we're really protecting it well. So that's the select category. Next, I want to protect the sensors. If maybe we picked a steel face, but it's still failing from physical damage. So maybe we have to think about excessive physical damage. How do we protect it from that? Or maybe we have excessive weld spatter. How do we protect it from that? We have a couple of solutions for that. Here you can see a bunker block. The bunker block is just a big hunk of metal to give more protection from physical contact for the sensor. Here's another version of the bunker block we call bunker block 2. That protects it. What's nice about this one is it allows position adjustment. So if you need to be able to move it back and forth, the first one has a positive stop. So the sensor hits a certain place and stops, where this one allows position adjustment. And then if you're having a lot of physical contact on the sensors and you want to put in a mechanical plunger, it's a really nice mechanical plunger that what we can do is we can actually allow for over travel. So you spin the sensor up and down to give you the switch point. And then when we clamp, it actually allows for it to travel, over travel. So it gives us more capability and more detection capability in a really harsh, rugged loading application and physical damage application. And then last but not least, when we're talking about protection, I love the quick change prox mount. Yes, it provides protection. It can be a heat sink for an inductive prox if it's kind of a warm application. But it also has a quick turn nut. You quick turn the nut, you could slide the prox out, you immediately slam in a new prox, you turn the nut, and it's sealed in its application. It's gapped perfectly. No one has to sit and adjust where the position of the sensor is. It's right in the right place every time when you have to change it out. So these are all great protection tools in your portfolio in a welding environment. Third is connections. We got to think about, is the cable collecting spatter? Is the connector not meeting the proper bend radius? What temperatures and environments is the cable exposed to? And then are you having networking devices or networking communication losses? So the first thing I want to talk about is cables, right? So there's lots of different options here. We call them the high durability portfolio, so the high durability cables. The first one that we see used the most is the silicone cables. This is a full silicone jacket on the cable. It has the smallest, one of the smaller ODs of the cable. And the silicone cable also has a nice weld-resistant molding material as well as a coated nut for resisting weld spatter. Then for people who don't like silicone in their plant, some people don't like that, we actually have a FEP cable, which is like PTFE or Teflon. And the FEP cable is a non-silicone cable jacket option for weld spatter resistance. There's also a couple of other versions. Some people like to have the silicone tube. It provides a thermal barrier for the sensor cable. They come in black or yellow. You can see both options here. And all of these cables have the special weld-resistant mold material as well as the weld-resistant nut. So there's a lot of different options there, as well as splitters to provide different options for what you're trying to do for connectivity in the cell. Next, if you're having network failures, like I mentioned, these are network blocks that are made of special material, Fortron material. This is a material that's weld-resistant housing. It allows you to protect the block and have it survive more in a welding environment. But I like to say, let's get the network up out of harm's way, in a rafter or out of the welding environment. We send an I/O link device into the weld cell, and that allows the network to always stay communicating and allows for faster troubleshooting because we send the device into the hazardous area with the welding debris and the weld spatter, and we leave the master and the Ethernet connection outside of the welding environment, and we just send a cable to collect the I/O. So this is a really great solution for us. So when we're talking about IO-Link, because I mentioned IO-Link, I want to make sure I point out a few features of IO-Link that are really beneficial to the weld cell. And the first thing is the IO-Link master. IO-Link masters talk over Ethernet, so you could talk about Profinets, EtherCAT, CC-Link IE Field, Ethernet IP. So Ethernet protocols. And what's cool is the master can use a standard sensor cable to communicate back to the IO-Link device. Here, we're using this as an I/O device. So this is collecting basic sensor information. And the basic sensor information, just like an I/O block that you would have in a weld cell, is all collected together and sent over this standard sensor cable back to the master. What's nice about this is you can get diagnostic information, like you can get short circuits here, right? So if you get a short circuit from a weld spatter or a weld BB on the cable, you can actually diagnose that this exact cable is the one that has the short circuit. And so that allows you to change out faster and execute faster. So that's an I/O block. but other options are out there. This here is a valve manifold. The valve manifold is a standard D-sub valve manifold with, that controls all of our clamping cylinders. But this connector, this valve manifold connector, actually allows us to connect back to the master and control the complete valve manifold over that connector. Also, many of the valve manufacturers make an IO-Link valve manifold. So then what you get if you have an IO-Link valve manifold is you get all kinds of diagnostics and information from the valve manifold itself, and that information can be reported back through the IO-Link master. Then what we're also showing is the SmartLight. This is great for indication, right? This allows us to do things like work in production, a normal stack light status, like is the machine running, is it idle? We can actually use it for doing tack time. So it can be used to indicate how much time is remaining in the process for the operator. How much time do they have to load the parts into the cell? So we can actually use it as a tack time indicator. Then over here you see a power supply. This is an IP67 power supply. What's nice about this is you can mount it right on the machine outside of the cabinet, and this allows a maintenance person to look and see, do we have good power supply? You know, power supply can be one of those things that's tough to troubleshoot. So if we have it out on the machine, they don't have to open the cabinet and risk any issues like arc flash or anything by opening a cabinet. So we can have the power supply right on the machine, and with an IO-Link connection on the power supply, we can get information like how much current am I drawing or how much service life is remaining. We can get warnings like how much time, how much life remains in the power supply. Maybe we need to change it out in the next machine cycle. Because every power supply has capacitors that go out over time. So wouldn't it be nice for the power supply to be able to tell you how much time it has left? So IO-Link has all of these great capabilities, like even smart sensors, like this BOS23K here. We can get diagnostics from that, like lens is dirty or lens is damaged. I'm still functioning, but hey, something's wrong with my lens. Maybe someone needs to wipe it off, or maybe it got a weld spatter on it and it needs to be replaced. But it'll still function and give you a, hey, something's cloudy on my lens indication, which is good. So that's IO-Link and total for a weld cell. There's lots of great applications here that we could go over. Shashir's going to talk about IO-Link for the smart factory. So if you're interested in how this connects to IoT, check out the presentation from Shashir on IO-Link for the smart factory. The fourth step is to learn. You know, we got to look at this. What caused the eventual failure? We need to analyze, was it heat? Was it spatter? Was it impact? And maybe there's multifactorial things going on here. What else is damaging the sensor? And then where else do we have similar installations? You know, you may have a couple of unique applications, but I bet you have a lot of repeated applications. So if you're having an issue and you've solved the issue with one of these technologies, think about where else do we have this installation, where else do we have this problem, and how do we duplicate it? I know it sounds like an obvious thing to do, but a lot of people, they solve the one application in the one moment, but don't think about how they can repeat that. And then again, how do you write your equipment specification to avoid this in the future? And how do we train our teams to identify these issues and improve them? So not only do we have to select the right material, we have to provide the right connections, we have to protect the product, but we also need to learn from the experience and make sure we're expanding the learning and doing that. And the way we do that is our fifth step. We document. Right? We need to analyze the applications. We need to document sensor failures. We really recommend that you utilize a system like this where you have a card that goes with the failed sensor. This one you could see weld spatter destroyed the face. So you attach the card, you have the operator or the maintenance person fill out where did this sensor fail, why did it fail, and you put it in a special bin and you analyze and document what are the sensor failures that are going on, where are they happening, where are our hot spots, and that way we can audit our high downtime areas, figure out better solutions and better technologies that fit in there. And when we do that, what we want to do is we want to document the return on investment. How many failures do we have of the old solution? How many failures do we have of the new solution? And then calculate, you know, what was the downtime cost? What was the labor cost? What was the product cost of the old way versus the new way? And if we look at that, time and time again, we can see annual application savings in the tens or hundreds of thousands of dollars a year for customers. So if you're looking for ways to save that kind of money and boost your productivity, reducing downtime, this is a great way to actually do that systematically by analyzing our applications and calculating the ROI. So just as a refresher, the 5 steps are we want to make sure we select, we protect, we connect, we learn, and we document our solutions, and that will help you achieve operational excellence. And those are the 5 steps to creating operational excellence in robotic welding automation. I'm Will Healy.